Hello everyone, this is our SciScreen presentation on Kessler Syndrome and the trials and tribulations of space debris. We are ScotSci, a science outreach program based in Edinburgh, Scotland, and we typically would group these events with a film. The film that we'd recommend that sort of ties in and kind of reinforces the message of this talk is the film Gravity by Alfonso Cuarón that came out a few years ago. Every now and then, you'll see a news article about some country blowing up a satellite as a form of a test, or a satellite failing, or a satellite being destroyed by a collision in space. These articles usually get surrounded by other mentions of space debris before everything eventually goes back to normal. This talk aims to illustrate why it's worth paying attention to these articles, but also that Kessler Syndrome itself isn't specifically like a doomsday scenario. It's in a way like climate change, where if it's handled sooner rather than later, it has a much lower chance, if any, if being completely negated before it can ever really amount to a serious problem. This story begins in October 1957. People on Earth will be treated to a sight that is now fairly commonplace. An artificial star, a small point of light moving across the night sky. Today, they are generally satellites orbiting the Earth, monitoring weather, facilitating communications across the globe. Back in 1957, people believed they were seeing Sputnik, the newly launched Soviet satellite. However, what they were really seeing was the empty shell of the R-7 rocket that had taken Sputnik up into space. And in doing so, this had become the first piece of space debris left orbiting the Earth. Fast forward over 65 years to the present day. You've had famous NASA missions such as Apollo and Voyager, deployment of ever more complex space telescopes, military exercises, and thousands of satellites launched into low Earth orbit or geosynchronous orbit. Each of these would have needed a way to get up into space, and then for those that had a specific task, a way to move into position so they could perform whatever objective their creators had in mind. This led to empty rocket stages, shielding, frozen coolant, and even small bits of metal that broke off or came loose during launch, all ending up in Earth orbit, until something either knocks them off course, or if they're close enough, the upper edges of the Earth's atmosphere will add a little bit of drag, causing them to re-enter the atmosphere and hopefully burn up. So as each of these pieces of debris float through space, they're exposed to solar radiation that causes them to degrade even further, eventually causing tiny pieces to break off. Or they will occasionally collide with other pieces of debris, and when this happens, you can end up with potentially hundreds, if not thousands, of new pieces of debris orbiting the Earth. Over time, this continues, and the number of pieces of debris in orbit continues to increase. If it continues, eventually there will be so much debris in orbit that it would disable or destroy any satellites already up there, and also threaten any future launches. This is the event known as the Kessler Syndrome, where there's so much debris flying through space and breaking off and creating even more debris. Humanity is essentially trapped on Earth due to this giant cloud of shrapnel surrounding the planet. You'd have no satellites to facilitate long-distance communications or measurements, and these would potentially remain in orbit for decades, if not generations, before they slowly got pulled down into Earth's atmosphere and burnt up. So where does Kessler Syndrome get its name? It is named after Donald Kessler, who is an American astrophysicist and former NASA scientist, who developed the idea that would become known as Kessler Syndrome while working at the Johnson Space Center in Houston, Texas. His idea was first published in 1978 under the exciting title Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. And as a result of that publication, he was made head of a newly created Orbital Debris Program Office in order to study and establish guidelines to slow the accumulation of space debris, in effect to try and prevent the problem he had just identified. He eventually retired in the 90s, but still remains active in the field and does talks on the subject. So now that you've been introduced to this somewhat apocalyptic sounding syndrome, what effect does it actually have? You'll probably think to yourself that like tiny pieces of copper wire or little bits of metal or paint can only do so much damage. Meanwhile, the larger abandoned rocket sections are large enough that you can surely just avoid them. The big problem is that most of them are traveling at extreme speeds, up to 28,000 kilometers or 17,500 miles per hour, compensating for having a tiny mass with a lot of energy, which will cause anything they hit serious problems. So how dangerous is the space debris really? In a word, extremely. The vast majority of the debris in orbit are tiny pieces measuring 10 centimeters or less. What they lack in size or mass is made up for the extreme speeds with which they travel through space. For example, the Cosmos 2251 Iridium-33 collision mentioned earlier occurred at over 42,000 or 26,000 miles per hour. In terms of how much energy is in a collision, a piece of debris about 1 centimeter in diameter would be akin to standing next to an exploding hand grenade, while a 10 centimeter chunk would be around the same as 75 kilograms of TNT. On average, one satellite per year is destroyed by space debris, and in turn adds to the amount of debris currently in orbit. For example, in 2009, the defunct Russian satellite Cosmos 2251 collided with the solar panel of Iridium-33, an American satellite. Iridium was sent tumbling out of control while Cosmos disintegrated. It's estimated that about 10% of the debris that's accumulated over the last 65 years was a result of this one single collision. Last week, China's Xinhua science satellite came within 14.5 meters, about 47 feet, of a debris cloud from Russia's anti-satellite test in November 2021. So technically, we can avoid them, given enough time and information. Today, all launches are planned alongside a radar map of all the currently known debris and their orbits, in order to make sure that nothing collides going up, and where the problem pieces are likely to be while the rocket or crew are in space. These maps are generated by special radar telescopes that track low or Earth orbit debris, while optical telescopes are used for more distant objects. They can also make use of optical telescopes that monitor the sky for like a 24-hour period to measure just how much debris they see in that time frame to provide statistical data, but also allowing the identification of new debris as small as 1 centimeter and potentially what that debris consists of. The ISS, the International Space Station, has the added problem that it is permanently in space and therefore has to deal with space debris on a regular basis. For example, this is a picture of the Canadarm2, which the ISS uses for servicing and maintenance, after being hit by debris in May of 2021. Luckily, nothing needed to operate the arm was damaged, so it is basically a superficial wound. Chris Hadfield has mentioned in interviews how you can even hear the sound of impacts on the station when everything is quiet, sort of like bullet ricochets and impacts. The solar panels used by the ISS are also regularly require maintenance, as they are effectively sandblasted by tiny debris particles. So how do we keep the astronauts safe? So to keep the ISS safe, we firstly have a safety zone, which is sometimes described as a pizza box due to its shape, which extends 25 kilometers or 16 miles off each side, and it's about 1 kilometer or just over half a mile tall, with the ISS at its center. If a piece of debris is predicted to come within this zone, the ISS will use its maneuvering thrusters to move itself away from the current threat and make sure it doesn't move towards anything else more dangerous. As you can imagine, the more it has to move to avoid debris, the more it needs to be refueled, which means more launches into space. Second, there's a special type of armor they've installed on the station called Whipple shielding, named after the astronomer Fred Whipple, which consists of spaced layers of material with the design idea that anything that impacts on the outside surface would break up on impact, and therefore the next layer along would be impacted by lots of smaller, slower moving pieces of debris. Unfortunately, they can't use solid armor like you would have down on Earth, because it doesn't really work too well with the speeds and energies of the objects moving in space, and it's also very, very heavy, which makes it very expensive and practical to launch, and also to then bolt onto the station, which may need to move at a moment's notice. And lastly, if there's a big enough chance of a collision, I believe this is about a 1 in 10,000 chance, the crew also retreats to the Soyuz capsule, which the station uses as an escape pod, just to provide some extra protection, and in the case of a breach on the station. So how do we solve this problem of growing space debris? This is a tricky problem to solve that various space agencies are working on, because the problems themselves aren't just technological. There's a lot of murky political territory to the efforts to combat the problem, as you'll potentially be dealing with another nation's military or communications equipment. There are some space treaties that basically the responsibility of objects in space are the responsibility of the government that launched them, which is about the one control that they do have currently. The challenge technologically is that there's not a huge amount of investment in technologies to either degrade space hardware after launch or retrieve existing debris. So most efforts currently are proof of concept rather than anything near final designs. For example, the Surrey Space Centre launched RemoveDEBRIS, a platform that tested different methods for capturing debris of different sizes, such as capturing debris with a net and a harpoon before finally deploying a drag sail that causes orbit to degrade and then burn up in the atmosphere. One of the biggest tests for this new technology so far is the European Space Agency's ClearSpace 1 mission, announced in 2019, which aims to neutralize the VESPA, Vega Secondary Payload Adapter, an upper stage left in orbit after the second flight of the ESA's Vega launcher back in 2013. VESPA is similar in size and weight to a small satellite, so should be a good grounds for a test. The aim is to launch in 2025 and ensnare VESPA using robotic arms attached to the ClearSpace 1 before propelling itself into a controlled atmospheric re-entry. The downside to all of these approaches is that you have to get these platforms up into space, which may involve adding some debris as a cost to removing larger potential sources of it. Alternatively, you have a system known as a laser broom, not exactly the most exciting name in the world, but it uses a ground-based laser system to fire a beam at a tracked piece of space debris in orbit. The aim is to use the power of the laser to apply a small amount of force to the debris, causing its orbit to change, and therefore more likely to cause it to burn up sooner in the atmosphere rather than later. So what can we do in the meantime? Part of the reason things are as bad as they are is that you have a lot of debris in the same orbital distance, meaning that for available space, there's a very large amount of debris going around. If you look at the debris in orbit at higher distances, such as like geosynchronous orbits, there's a lot less debris going around for the space available. So the current plan with further launches is for devices to be able to change their orbit at the end of their lives, either through controlled re-entry into the atmosphere, if they're low enough, or to move to a higher orbit, referred to as a graveyard orbit, where there'll be another way of active equipment, which doesn't necessarily solve the problem. It does mean that the debris poses a lower risk to the devices we really need. The alternative is efforts like astroscale, where you apply like a magnetic docking plate to your satellites and other equipment, so that at a later date another launch device can attach to the magnetic seal and therefore move the debris around to where it's needed if it's not able to move itself. If you are interested in seeing representations of space debris, because a lot of what there is exists as data that needs to be interpolated by someone else so you can actually see it. You have efforts like Stuffin.space, which gives you a basic representation of like the more interesting parts of like orbiting satellites or debris for sort of historical purposes. For example, you can see the pieces and orbits of the different parts of the Iridium-33 Cosmos 2251 collision. You can see the orbits of the US GPS satellites or the EU's Galileo satellites. There's even trackers for the Westford Needles, which were from Operation Westford in 1961, where the US launched 500 million copper antennas to try and ensure long-distance radio communications if the Soviets ever cut the ground cables between continents. Some of these never dispersed, and they remain in orbit to this day. You can also track like the various SpaceX launches since 2010, I believe. And one of the Falcon 9s is even the one that was mentioned recently in the news that is on its way to a date with the moon's surface. Anyway, thank you for watching and listening, and I hope you know a little bit more about Kessler Syndrome and space debris as a result of this talk. If you have any questions, feel free to ask below in the comments, or you can tag us on social media at Scott Syed on Twitter or Scott Syed Edinburgh on Facebook, and we'll do our best to answer your questions. Thank you very much.